Hello and welcome back to Calculus 1, section 5.2, also known as Hell on Earth. Yeah, I'm just kidding, but yes, it is. Computation-wise, at least. So we're going to have now a way to compute first we're going to derive what this definite integral is through the area calculation. Then we're going to have these calculations with these summations, and then we're going to say, but wait, we can do it this way as well, and then you're gonna go, whew. So we're gonna start nice, make it terrible, and then we're gonna bring it back, and then we're gonna all be friends at the end. All right, so hang in. All right, hang in and follow. We are going to start with the idea we had last class, where we said that every area under the curve is calculated by those rectangles, and the more rectangles you put, less error you have. So if I draw, let's say, this as a shape, it doesn't matter what we draw, and then I put, right, 4 rectangles, and then I put, divide those in half. You don't have to do it in half, you can divide whatever way you want. And then you divide those in half. Again, it doesn't have to be divided in half, you can add 15 lines if you want to. And then keep dividing. Eventually, as the number of rectangles start going to infinity, you're going to see that all that's going to happen here is it's going to be so dense, right? Now, this is not proper mathematical talk, but this is what's happening, right? It's going to be that like every point over here of this line, which is infinitely many points, will have a rectangle of the width near 0 or 0 underneath it, and then since it's only 1 point wide, there will be no error. So remember what we had. We had that the area was approximated by delta x times summation I goes from 0 to n minus 1, let's say, of f of xi. So when you pool any one of these, which we can call representative rectangle, you just pick one. That representative rectangle has xn on one side, xn plus 1 on the other side, and has the height of f of xn. So that one has the area, so area of this one representative rectangle is the difference of these two is delta x times the height. So you would say f of xn times delta x, because delta x can be found by b minus a over n, but can also be found by figuring out xn minus 1 minus xn, right? Whatever those numbers are. So if this is, let's say, 4 and this is 3, then 4 minus 3 is 1 and delta x is 1. So if you have those numbers, you can find delta x, but also if you have the entire interval and then you have how many rectangles you have, you can find it that way as well. Okay, cool. So now, what's the deal for this? Well, this sounds good. Now, I can actually figure out the exact area this way, because, as I said, if I make somehow, right, if I am able to stuff infinitely many, infinitely thin rectangles between A and B, those rectangles will be so thin, infinitely thin, that they would fit under each point of the function and we would have no error. So that has to be an exact area. Now the question is, how do I fit infinitely many rectangles inside a finite interval that is, let's say, 2 to 4? Well, hold on. you already have infinitely many points between 2 to 4. Just think about it, right? I understand that 4 minus 2 is equal to 2. Fine. But how many points are there between 2 and 4? How many points are in between any two numbers? And its answer is always infinitely many. Because those decimals keep subdividing and subdividing and subdividing. So you say, oh, okay, well, 2.5 is in there. And I say, yeah, but so it's 2.51. And then you say 2.511. And I say, no, 2.5111. Right? And you can see that you can keep adding the decimal 1 forever. And literally any location you pick, right? Any two locations you pick, you will always have infinitely many values in between them. Okay, so now that we actually understand, and we kind of knew this, that we had infinitely many numbers on this line, it shouldn't be a big stretch for our head to say, well, how about if we, under each one of those points, there are infinitely many, how about if we stick underneath one infinitely thin rectangle whose width is practically 0, right? And because now I have infinitely many points, I actually have infinitely many rectangles. Well, that sounds good, right? So that's awesome. And how do I now build what it's called a Riemann sum by mathematician Riemann, who worked on this stuff in 1800s? How do I fit this in my equations? Okay, let's take our representative rectangle. So we're going to have a couple of these rectangles lined up. There is the function f of x on top. And we're going to go with this one, which is, let's say, xn plus 1 with the delta x in between, and the calculation on the function of f of xn. So, as I said before, you start thinking about this and you say, actually not xn, sorry, xi. We use I, not n. xi. The book that I learned from uses n. This book uses I. And then the old book used n also for Calc 2. This book uses k for that one. I was like, be consistent, but whatever. So xi. So what is my delta x from this picture? Well, it's xi plus 1 minus xi. So I can calculate delta x easily. I don't have to worry about that, because those are given right on this picture. And the area of the single rectangle is going to be f of xi times delta x. So this is what I'm going to label as one rectangle, right? One rectangle. Now, this is some xi rectangle, which is literally whichever one you pick. But then you say, okay, this is the area of the single rectangle, which is what I learned when I was in a second grade. I have a lot of other rectangles in there. Maybe I have 4, maybe I have 7, maybe I have 19, whatever amount. Okay, let's fix that. Let's say that you have rectangles 1 to some unknown number of rectangles, say n. Because I'm going to open it to you to put as many rectangles you want. And now, with adding the summation, we say many rectangles. And this is your approximation already, which is technically your 5.1 section, right? This was your elementary school. So one rectangle is just elementary school formula, a times b, and you're done, where your a is delta x and your b is the function given by, height given by function. But then now when you add summation, we say, okay, well, maybe we have 4 or 10 or whatever amount of these, and that's your 5.1. The only thing that it's left for us to do is to say, well, I don't want a finite number of rectangles like 8 and 10, because I want them to be infinitely thin, and I want infinitely many of them to fit in under each point of the function. I'm going to send the number of rectangles to infinity. And now, with this, you have exact area. This is what we are dealing with in 5.2 and on in calculus. So we are able to calculate this now, and this has a very this has a name attached to it, which is Riemann sum, and it is used to calculate area under the curve. Now, it's going to give us the exact area. So, Riemann sum is equal to the limit n goes to infinity, summation I goes from 1 to n of f of xi delta x. There you go. And this is going to compute exact area. Now, let's check, because we can, right? So, find area under f of x equals 2x squared minus 4x plus 1 on interval 1 to 4. Doesn't really matter. I just made up everything. It really doesn't matter what you pick. So now, this calculation is going to take some time, a lot of steps, but let's do it. As always before, we are going to start this calculation by calculating delta x, which is b minus a divided by n. In our case, 4 minus 1 divided by n, which is 3 over n. You're going to say, wait, we always had that n before. Yes, but now this n goes to infinity. Because remember what you are trying to get. When you have your rectangle like this, you are trying this delta x to go to 0. You are trying to make it infinitely thin. And that's very easily achieved by 3 divided by infinity. I hope you guys see that. Because if I put this n to be any finite number, like a million, or you think that 100 billion is a big deal? No, it's not, because you can always find much smaller number than 3 over 100 billion. So 3 over 100 billion is nothing for subatomic particles, okay? Nothing. It's like, wow. So the idea here is to leave this n as n, because that n is going to infinity in our formula, and because it's going to infinity, it's creating this infinitely thin rectangle, so that when you have the point, some point xn, right, this rectangle fits underneath it like a line. I mean, this is a terrible thing to say mathematically, but if you're trying to visualize this, just think that infinitely many points and each one has literally a line thick, which is no thickness, technically rectangle underneath. So now I have delta x. Well, great, that plugs in here. How about the rest of the problem? Well, I see that I need this xi business, right? And that needs to also be addressed, because xi is a plus I delta x. Now, this is technically a formula, but think about it. How do we address x0, x1, x2, x3, right, going through one by one? Well, the x0, we know that's a. And then there is delta x here. So to get to x1, all I need is a plus delta x. Now, to get to x2, I need 2 delta x's. Okay, so if I start at a, which is my x0 starting point, and add 2 delta x's, I will get at x2. So I hope you see how this I counter becomes 1, 2, 3, 4, 5, 6, 7, right, to give us x1, x2, x3, x4. Because every time when the counter jumps at x3, I'm starting at my a, which is x0, which is the home location, plus 3 delta x's are added. And then we're going forward. Perfect. So now that we have this sorted out, some students like to circle this as a formula because it literally shows up in every problem the same way, just like your delta x is showing up in every problem as a formula the same way. Fine. But in our case over here, we know that our a is 1 plus I times 3 over n. So this mess is 1 plus, now when I say 3i over n, it's not a complex number. I is a counter, not a complex number. And I gotta write that in, I want to write it in blood, but then it's going to clash with my formulas. So I is a counter, not complex. Please don't confuse, because I know that you know 3 plus 4i, right? And that's a complex number. But in this case, that's not it. It is the counter, and that counter is 0, 1, 2, 3, 4, 5, right? Where complex number I means square root of -1. So they're completely different ideas. Please don't confuse those two worlds. We are not dealing with complex numbers in any shape, way, or form in calculus here. So now we have the next part, which is where we plug all of this into our equation. So the exact area, see, now equal. It's no longer squiggly here. It's exact. Okay? So no squiggly sign is a limit. N goes to infinity. Summation. I goes from 1 to n. And now, oh, I didn't create f yet. Can't plug in yet. Move that down. In your case, erase it or burn the page or whatever. I forgot to create f of xi because I don't know why. F of xi. Well, I know what xi is, and I have what f is. So 2xi squared minus 4xi plus 1. Okay, that's 2, 1 plus 3i over n squared minus 4, 1 plus 3i over n, and then plus 1. Boom. Let's go and get this simplified. So I have 2 times And now I have to FOIL all of this, which is 1 plus 6i over n plus 9i squared over n squared minus 4 minus 12i over n, and then finally plus 1. And now simplify everything in 1. 9i squared over n squared. That's this one. Then, oh no, that's not 9, that's 18. Please pay attention, guys. Call me on these things, because 2 multiplies into everything. So 2 times 6i, and then minus, there's 12, and then minus 12, that's gone. And right, 2 times, oh wait, oh no, that was good, that's good, that's good. So 2 times this is 12, and minus that 12, that cancels. And then I have a 2 plus 1 is 3, minus 4 is minus 1. I hope this simplifies into this. Now, obviously, if this is wrong, everything else is going to be wrong. So let's go and check everything one more time. So when I plug in my 1 plus 3i over n into this, I get that one minus 4 times and then plus 1 over there. Okay, cool. So now plug in, when I square it, it's a squared plus 2ab plus b squared. So yes, 6i n, and then a 9i squared n squared, and then minus 4, and then minus 12i over n, and then plus 1. Good. So that's 18i squared over n squared. 12i minus 12i, that's gone. 2 minus 4 plus 1, negative 1. Okay, we call that good. So what do I have? I have this times 18i squared over n squared minus 1 times 3 over n, which is delta x. So this over here is your f of xi. This over here is your delta x, and the rest of the formula is directly from the formula as is. And all I need to do is to solve this, and then we have our area. So what's area equal to? Well, limit n goes to infinity, summation I starts 1 goes to n, and then I have this to distribute. 18 times 3, that's 3 times that's 24, so that's a 54 I squared over n cubed minus 3 over n. Nice. Now, properties of sums. We do have course at RV that it's like a 1 credit honors course when you learn these properties and so on. So now you give to each one of these terms inside its own sum. There we go. And now we have to solve the sums. Now, these formulas, very easy to remember in our book. Page 345 is where the formulas are on how to simplify this. But first of all, I need to make sure that you see how to simplify this. You can kick out 54 over n in front of the sum, and you have your I squared stay. And on the second one, you kick out 3 over n out. Oh, this is 3 over n cubed over here. 54 over n cubed. And the second one, when you kick everything out, 1 stays behind. Now, why am I able to kick this out? Guys, remember that you always had, when the variables, parameters or whatever, are inside your limits, derivatives, and the integrals. We saw that last class. You can always kick them out. Now, for the limit, right, when you are working on the limit as age goes to 0, you don't care that x is around, right? X is not a variable in the eyes of that limit because limit operates on age. Age goes to 0. Same thing happens that if you are taking, let's say, the derivative of ax squared. The derivative is you copy a and then you have 2x and then it becomes 2ax, right? The derivative did not bother this a, you did not do the product rule or anything like that because the notation of the derivative tells you that x is the variable that you are worrying about. Anything else that shows up in that problem is a constant, it's a parameter. So the same thing happens here for the sum. You see, the variable that the sum operates on is I. So when you are looking at the entire thing here, the I is the variable. The rest is a constant, which means you can kick it outside in front of the sum. So as I said, the same rule that we had before for all other things, right? So now, when you use the formulas provided in the textbook on page 345, this the summation of I squared turns into n plus 1, 2n plus 2, 2n plus 1, divided by 6, minus 3 over n, and this one becomes just n. Now, I am going to just do this. Oops. So the orange stuff is at work over here. So now you are back to first section of your calculus, right? Where you have 54 over 6, I know it can be reduced, over n plus 1, 2n plus 1, over n cubed. We can cancel one of the n's right there, so we have less stuff to worry about. Minus 3. So, when you solve this, the limit for this is 2. If you learned your limits before, because the first term over here will be 2n squared. 2n squared divided by n squared is 2. So the limit is 2. So you have your 54 over 6 times 2 and everything minus 3. These guys can cancel. That's 54 over 3 minus 3. And then these guys can cancel because 5 plus 4 is 9. 9 is divisible by 3, therefore 54 is divisible by 3. When you divide it by 3, you get 1 and then 24, 8 minus 3. The whole thing is 15. So the area is 15. Now, this is the exact area under the curve. Yeah, it took some time to compute, right? But we got it. There it is. Boom. Now, right, this is on YouTube, so you could go and watch this like 15 times now. Now, what do we have? About 13 minutes. Probably some of you are panicking. What just happened here? Like, why is this problem 15 pages and I have no clue what happened? Well, when you practice and study, if you're interested in this, you will know what's going on and what happened. But there is a way out for us for this particular problem. Because what I can do is I can say, well, here is this problem that I had that I want to find the area for. And I'm just going to stick that into the integral dx. And I'm going to use my limits, interval 1 and 4 as limits of integration. Now, this is a new type of the integral you guys haven't seen. Now, something like this is called a definite integral. Now, you do know to integrate, you just don't know what to do with 1 and 4 yet. So we're going to do what we did the last class. That's 2x cubed over 3 minus 4 times x squared over 2 plus x. And here is this new part of the integral. We do not put plus c. When you have the numbers on the integral, when you have a definite integral, you would put this line which says compute at 1 and 4. Now, the way you compute this, well, first you simplify. So you get your 2/3 x cubed minus 2x squared plus x from 1 to 4. And the way you compute this is you plug 4 for each x. So we'll have 2/3 4 cubed minus 2 times 4 squared plus 4. And then you subtract by plugging in 1 in each spot. And you just compute this. Okay, that's 2/3 4 cubed. Well, that's 16 times 4, which is 64. So we have 2 times 64 minus 1632 plus 4 minus 2/3 plus 2 minus 1, because this negative has to distribute everywhere, so all the signs are backwards. Okay, 64 times 2 is 128. So I have 128 over 3 minus 2/3. And then I have all of these as common. Well, this is 1. So negative 32 and then plus 4 is going to be negative 28, and then plus 1, negative 27. Okay. This is 126 divided by 3 minus 27. Now, 3 into 12 goes 4 times. 3 into 6 goes 2 times. Minus 27. Oh, it's 15. Aha! So I can use integrals to find area under the curve, and I don't have to go through all those calculations up there. Again, this is a vanilla calculus class, which means, no, you don't get to compute this on a test. Boo-hoo. Now, if you would like to compute this on a test, let me know. I will include it on your exam. But for our honors courses, obviously, they have to compute this on a test. They have to know the formulas. They have to know the procedure. Now, you have seen what it takes to find exact area using Riemann sum. We were able to bypass all of that using what we call definite integral. So now, I don't want to hear any complaints, because your choice is A or B, right? Those are the two choices. And something is telling me that you will be choosing B, right? So, what we found out is that the exact area is given by the Riemann sum which is at the same time the same thing as definite integral that looks like this. Now, do we somewhat see correspondence between these two worlds? Like if I am to highlight a little bit right there, right, and circle a little bit right here, and then say, let's go green, I guess, sum, that's literally what this symbol is. It's a stretched S that stands for sum. And that's not a joke or a meme. That is actually what it is, because the Riemann in 1800s used this as a notation. I can never remember, did he use this? It's one of these two. I don't know if it was P and U, because I think it's in German, like upper and lower, or whatever the way it is, right? This was the notation like 200 years ago, guys. And over time, all we did is we said, you know what? Stretch this, put your P and your U, whatever, and then just said, okay, A to B for the interval. Yeah, that's literally what it is. So now you understand what integral actually means. Integral calculates the sum, calculates the accumulation, right? It's accumulation that it computes. And now in comparison to the derivative, which calculates the change, i.e. the difference. So derivatives compute difference, integrals compute the sum. Now, it is time to write the definite integral. And then the next class, right, we'll talk about the fundamental theorem of calculus, right? Gotta figure out how to make my voice really ominous when I say that. Fundamental theorem of calculus, which is going to connect literally everything we learned, which is derivatives and integrals. So, to compute this monster, if you call this monster, what you gonna call the other calculations? Right, the one with the summation, if this is a monster. To calculate this beauty, right, all you need to do is to compute your antiderivative just like you computed that antiderivative before. And now instead of putting plus c, you're going to put this vertical line, which means compute. And then you are going to do f of b minus f of a. This is your life. Right here. This integral you will be computing in every single course past Calc 1. Calc 2. Calc 3 is going to have triple integrals, where you're going to have like 1 and 2 and x and blah, right? So you guys are going to compute these integrals a lot. And what you see on the screen right now is something that if you don't know, your education in calculus is over. There is no way to say, I'm going to, make it work somehow. You can't. Definite integrals are everywhere. And as I said, over 60% of your calculus 2 is integration. Your entire chapter 6, every integral is definite integral. For the rest of the chapters, half are definite, half are plus c. But your chapter 6, every single one is the definite integral. So you really need to learn this well. Now, they're very simple. If you know 4.9 integrals, this is not going to be anything special because you're just adding arithmetic. That's all you're doing. You're adding arithmetic to it. So if you have to compute your integral, let's say from 0 to 6, and let's say just x squared dx, it goes x cubed over 3 from 0 to 6, which is 6 cubed over 3 minus 0 cubed over 3. That's all. That's it. There are no surprises here of any kind. Now, we will have to be careful about certain things, but that's next lecture. Right now, whatever is thrown at you, you know that from here to here is 4.9, and then from here to here is the formula up there, 5.2. Just this stuff. That's all it is. We are not learning new methods of integrating or anything. You are learning how to compute this, what we call upper and lower limit, which are literally your a and b on x-axis, the limit where the area is. But I'm going to draw the picture next, right? We have a few seconds. So this is, okay, 6 cubed. Well, this is 0, so I don't have to worry about that one. But 6 cubed, I don't want to go 6 times 6 times 6. What I'm going to do is I'm going to cancel one of these, get a 2, and 6 times 6, 36 times 2 is 72. Done. Now, what is the meaning of this? The meaning is very simple. Here I have the x squared curve. 1, 2, 3, 4, 5, 6. And this area here is 72 units squared from 0 to 6. That's what it means. So if you are connecting your area to integrals, you are going to have some function f of x, which is going to be cut between a and a b. This is your area in question. And that area in question is going to be given by integral a to b of f of x dx, which eventually is computed by that f of b minus f of a. Now, we are going to expand a little bit on this and include something you have to be careful about next class. But for right now, you go into 5.2 homework or anything, and they just have a whole bunch of these integrals. I'm trying to find where this thing is. And you're just supposed to solve them. So let's see. For some of these, they're asking you to be clever, and for others, just use the brute force. So this is problem 42. It's going to take 2 seconds. I know the class is over. If you have to go, you have to go. But this is going to be very quick. Here's a problem, right? And I know that the integral of 1 is x, integral of x is x squared over 2, and all of this needs to be computed from 0 to 2. Plug in 2 everywhere, that's 2 minus 2 squared over 2, minus plug in 0 everywhere, 0 minus 0 squared over 2, which gives us 2 minus 2 minus 2, and that's equal to 0, right? So now you're going to say, I don't like the answer because I'm supposed to calculate 0. I'm supposed to calculate area and I'm getting 0. And if I draw this function, it's probably not going to be 0. Well, yes, you're right. And that's what we are exactly going to discuss on our next class on Monday. So yes, I'm leaving you with a cliffhanger there to go and say, wait, I can graph this function, right? Why do I get 0? Right? Because clearly there is an area, right? Sure, graph it, check it out. Maybe you're gonna go and look it up on your own, but this is exactly the situation we will be discussing on Monday with our fundamental theorem of calculus. So see you all Monday.